Hi pre-calculus class. We're starting here with chapter 9. And the next 2 days I've recorded these videos to hopefully better instruct the notes since I'm not here. You'll be given the note packet. So we've got a note packet again for chapter 9. Chapter 9 has nothing, well, it does have somewhat to do with trig, but not trig identities, not the orange card a bit, maybe a little bit, but not as intensely. It's exciting because this is something completely new, completely new. We're going to learn how to graph on a totally different coordinate plane. So the only graphing you've pretty much ever done in terms of a plane is the x and the y-axis. In terms of two-dimensional. We're still going to be graphing two-dimensional on a plane, but we're going to be graphing within what's called the polar system. So we're graphing in the polar system. It's a really short mini unit. We're just doing 3 lessons. We're just kind of brushing the surface of it, but it is some curriculum or content that it is expected that, as you move through higher level mathematics, that you should be exposed to it at some point. So Mr. Olson and I thought pre-calculus is a good place for us to introduce the idea of polar graphing to you. So it's a completely different graph paper. When you do these assignments, you're going to need to pick up polar graph paper, which is over on the side stackers where I keep all the graph paper. So we've had X and Y axis graph paper, we've had trig graph paper. Now you're going to be using polar graph paper. So here's our objectives for 9-1, and it's kind of lengthy. We're going to understand what is a polar coordinate. What does an ordered pair look like in polar graph? We're going to graph a point in the polar plane. We're going to understand multiple representations of a polar coordinate, and then we're going to do some simple graphs, some simple polar equations. Okay, so totally new. I'll try to take it slow, talk through it, again and again. But don't be, if you don't understand something, please get some extra help. Seek some extra help from each other, Math Lab, all those good places. All right, first of all, what are polar coordinates? That's a point. The location of a point P in the polar coordinate system can be identified by the polar coordinates in the form r, theta. So when we write an ordered pair, we don't call it an ordered pair. We call it the polar point or the polar coordinates. It's not x, y. It is r, theta. R, theta. Again, theta representing an angle. Okay, so what do the r and the theta represent? The r and the theta represent how we're going to graph those values on this plane. Okay, so down here, the origin is called the pole. So this point right here in the middle, the origin, that has a special name and it's called the pole. The origin is called the pole. The positive ray of the x-axis is called the polar axis. Okay, so that's this. So the pole is important and this ray is important. It's called the polar axis. So in terms of important pieces of information to help you guide graphs, the pole is this point here in the middle, the origin. The polar axis is the positive ray of the x-axis. Okay, in this coordinate, in this point, r is going to be radius. It stands for the radius. And it's the distance from the pole. Distance from the pole. So radius is going to be how far out are you counting on the circles, the radius from the pole. Theta is obviously an angle, but where? From what? How do you measure theta? So you measure theta, the angle, in standard position from the polar axis. From the polar axis. So reminder about that. The angle is going to be the angle in standard position from that polar axis. Keeping in mind, moving this direction is positive angle measure. This direction is negative angle measures. So positive angle measures, negative angle measures. If you look at this point right here on this graph, point P, it's really hard to read, but point P on the graph there is the point 1, 2, 3. So I'm labeling this point right there. Do you see how it's 3 circle lengths out? So that's a radius of 3. 1, 2, 3. So point P on that picture would be 3 comma theta. What is the angle measure in standard position from there to there? You could either say 3 comma pi thirds or 3 comma 60, just depending if on your degrees or radians. So that point could be the point 3, a radius of 3, out 3 circles, 3 rings, and then the angle theta is pi thirds or 60 degrees. So on that graph, that is the point P of r comma theta, which is a radius of 3 and an angle of pi thirds. Okay, so let's go down here and graph again P comma 60 degrees. So interestingly enough, maybe we should have picked a different value because it's exactly the same, but now I'll plot it out so you can see it again. And we kind of hopefully made this big enough so you can see it. Okay, so here's your polar graph paper. So we're asking to graph point P on this grid, where this is the radius r and this is the theta 60 degrees. So when we do this, I actually graph the theta first. Okay, I find that part first. Okay, so starting here at 0, rotating to the standard position of 60 degrees, so I'm on that terminal side. Then I have to go out a radius of 3. So 60 degrees, standard position, a radius of 3. So there's radius 1, radius 2, radius 3. So on the 60 degrees, 1, 2, 3. There's point P. Okay, before we go to Q, I'm actually going to add another one. Let's actually label point R, and let's do negative 2 comma 135 degrees. So let's do point R of negative 2 comma 135 degrees. Wait a minute. Back up. Nope, abort. I see it's on the next page. Sorry. Back to this one. This is good. Okay, so there's negative radius on the back. So we've got this angle of, this says negative 5 pi over 6. So there's your r, there's your theta, and you do the theta first. So find that terminal location. So negative 5 pi over 6. Negative, we got to go backwards. Negative 5 pi over 6. So we're counting by 6. Here's 1 6, 2 6, 3 6, or 30 degrees, right? That's a reference angle of 30. 3 6, 4 6, 5 6. I'm right here at this terminal location. That's the terminal location I'm at. Backwards, negative 5 pi over 6, and on that terminal location, I have to go out 2 rings, radius 2. Put a dot right there, R. No, Q. So the angle of negative 5 pi over 6, or negative 150 degrees, if you needed to convert that, I guess so, but try to, force yourself to work in radians if you're in radians. 1 6, 2 6, 3 6, 4 6, 5 6, out a radius of 2. Okay, there you did. You graphed 2 points, 2 polar points on the polar graph. Radius theta. Do theta first. Find that terminal side first. And then just count out the circles. Okay, so flipping it over, what happens if you have a negative radius? So in these 2 examples, we had a positive theta and we had a negative theta. What happens if you have a negative radius? Okay, how does that impact our plotting? Okay, if we have a negative radius, okay, if we have a negative radius, what's going to happen when the radius is negative? You graph the terminal side like it's positive and then draw the opposite ray. It's like you're taking the terminal side, and if you're counting a negative radius, you have to go backwards on that terminal side. You have to plot the opposite ray. Okay, so let's just practice that. It's just easier if we just do an example. So here's the radius of -2, r theta. You always do the theta first. So find your terminal side of 120 degrees. So here's the terminal side of 120 degrees, positive 120. Now, this is the positive terminal side. If it were +2, I'd put a dot right there. However, it's a radius of -2, so you have to go straight back 180 degrees on the terminal side going opposite. So here's positive 120 degrees. If I have a negative radius, I have to look at the terminal side going opposite of it. So instead of going out +2 this direction, the point goes backwards 1, 2. So that would be point P. So this is the positive radius, but now I have to go still that same angle measure, just back from it, -2. So that's point P, 2 rings on the opposite terminal side. Okay, let's practice this one. R comma theta. R comma theta. Maybe let me grab a different color. R comma theta. Always do theta first. 7 pi over 4. 7 pi over 4 is in that 4th quadrant right here. This says 7 pi over 4, reference angle 45 degrees. Okay, so I'm right here as my terminal side. Positive 7 pi over 4, right there. However, it says a negative radius. So you have to take that same terminal location, just go backwards from it. So instead of going on that terminal line of +4, you take it and go straight back 180 degrees and count 4 circles. 1, 2, 3, 4. There we have point R. So straight back. So when you have a radius negative, instead of counting out on that terminal side, you just go back from it in that many circle rings. Okay, I think, hopefully that's okay. Okay, here's what's completely different about polar graphs versus graphing points on the x and y axis. This is what's so cool about polar graphs. When we graphed a point on the polar, or on the x and the y axis, you don't have to draw this if you don't, I'm just explaining something about x and the y axis. So if I asked you to graph a point on the x and the y axis, like 2, 5. Yep, 2, 5 right there. Is there any other way that I could get to that point besides calling it 2, 5? Any other way? Is there any other way that I could get to that location other than calling out 2, 5? There's not. The only way that you can get to that point is by calling out x is 2, y is 5. What's awesome about the polar coordinate system is that we can have a point graphed and it can have multiple names. So instead of one name for one point, we can have a point that has multiple names, multiple coordinates. And that's what we're going to do here. We're going to talk about the multiple ways to represent a point on the coordinate plane, or I'm sorry, on the polar plane. So we're going to learn how to give multiple representations of a point on the polar plane. And this just is multiple. We want to learn multiple ways to represent the same point. Now, this is the textbook definition. I think it's confusing. We put it in there because at some point it's good for you to get to be able, some exposure to this kind of mathematical print and reading of it, but it is definitely confusing. So the best way is to actually just talk through a graph and talk through all the different possible ways to represent the point. All right, so we're going to have the point, where is it? S, right here. So we're talking about point S, which is on our graph right there, S. And we're going to give it in degrees. So our thetas are going to be in degrees. And I only want our thetas in between positive 360 and negative 360. So that's one rotation positive and one rotation negative. Those are my only options for theta. Okay, let's first name point S, but name it in its easiest one. So this is the easiest. Positive radius and a positive angle. So all of these points are going to be r comma theta. R comma theta. Okay, so if we're naming point S, so all of these are multiple representations for point S on that graph. Okay, positive, positive, positive radius, positive theta. So I always start with the theta. It is a positive 150 degrees. And how many circle lengths is it out on that terminal side? 1, 2, 3. So it's 3 comma 150. 150 radius 3. All right. Now the next representation is cueing us that we want to do still a positive radius but a negative angle. A positive radius but a negative angle. So now we're going to go that way for our theta. So what is the angle measure that goes from here to here? Well, if you did 360 minus 150, because remember it was 150 positive this way, 360 minus 150 is 210. So we could say backwards, negative 210 degrees, but still out a positive radius of 3. Those two names of the point still land you at point S. Two different names, same location. All right, now, let's talk about negative radius. So if we're talking about a negative radius, we have to land then back here on this terminal side because it matches this. It's along that same line. But I need to be on this part of it in order then to have a negative radius shoot me back to point S. Okay? So how can I land here with a positive angle? So I'm landing on this terminal side, but that part of it, that terminal side over here is 330. That red's not very good. 330, so I'm here, but if I want to land on this point, then I go backwards, -3, a radius of -3. So I'm on this part of the ray, 330, and if I have a negative radius, it goes backwards from that. Now not on the positive side, step backwards on the negative side. So that's a negative radius, positive angle. And notice I'm keeping my angles in between -360 and 360. Okay, finally, last one. We want a negative angle, negative radius. So again, if it's a negative radius, I have to land here to go backwards onto that point. So if it's a negative radius, I have to land on that terminal side. But now it's saying I want a negative angle. So the negative angle that goes backwards would be negative 30 degrees and then negative 3 radius. So all four of these are representations of that point, just on different variations of positive radius, positive angles, negative radius, and so on. Now, the reason that Mr. Olson and I lay out these is so you can get the multiple representations with all kinds of different versions. Certainly, I mean, what would keep us from saying, well, if I want this point in multiple versions, why couldn't I just add 360 again, add 360 again, and just keep adding 360, and that would be another different theta? True. That's why we get real specific about how the different representations need to be, because otherwise you guys are really sly and tricky and lazy and easy. And you're just like, well, I'm just going to keep adding 360, and that's a different point. That's a different coordinate. It's a different coordinate, but it's too simple. You can do better than that. So we're going to ask you to give these types of different representations. Okay. All right, next example. Flip it on over. Name 4 different pairs of coordinates that represent point S on the graph with the restrictions that theta is going to be in between negative 2 pi and positive 2 pi. So now we're talking about radians. We're only going to use radian thetas, not degrees. And we're going to name point S in these 4 different coordinates. So again, r comma theta, r comes first, theta comes second. So we're at this point. I don't think that's right on my graph. Let me find out where it's supposed to be. On my paper notes here, I have 11 pi over 6. 11 pi over 6 is right here with its out 1, 2, 3, 4, 5, 6. So 11 pi over 6 is what's on my paper. And out 1, 2, 3, 4, 5, 6. Point S. Don't do that point. I don't know if, hopefully this is right on yours, that this is where yours is. 11 pi over 6 and point S. Okay, so the first one is the easiest one. Positive, so you want to be right here on this terminal side. So positive 11 pi over 6 radians. And out how many rings? How many radius? 1 radius, 2, 3, 4, 5, 6. 6 ticks. Okay, then they want you to give another coordinate for the same point, but this time a negative angle. So the angle that goes from here to here would be negative pi over 6. Or that's 2 pi minus 11 pi over 6, which is pi 6. Just go back 30 degrees or back pi 6. And it still is out a positive radius of 6. Okay, now the negative radii. If we're talking about a negative radius, we have to go on the terminal side backwards. I need this spot. And then it'll go backwards negative 6, the opposite direction of the 6. Okay, so how do I get a positive angle? This would be the positive angle. So the positive angle there is 1, 6, 2, 6, 3, 6, 4, 6, 5, 6. So we've got 5 pi over 6, positive, go opposite direction, a radius of negative 6. Okay, finally, we need a negative radius and a negative angle. So we still have to land on this terminal side to go opposite radius, but this time I want this much, which is going to be pi plus the extra pi 6. So it's 6 pi plus pi 6, which is 7 pi over 6. Backwards, a negative direction. So negative 7 pi over 6 gets you there. Opposite direction of a radius, boom, gets you right on point S. So it's negative 6 comma negative 7 pi over 6. For me, I mean, you can follow that little formula of plusing 360s, minusing 360s. For me, if I just have graph paper and I plot it, and I just visually look at spinning positive, spinning negative, going opposite, that's super helpful for me. So visualizing it all going on is way better than plusing and minusing some formula. So really, work on the visualization. Okay, next, polar equations. So we're going to graph some really just simple polar graphs to start with. Tomorrow we're going to get some really interesting ones, some really cool. So I mean, if you're curious and you want to kind of look ahead, yeah, you're going to see some really cool pictures. I don't know if we've got any actually drawn on there, but tomorrow's going to have some fun graphs. We're just going to start with some really basic ones, okay? An equation expressed in terms of polar coordinates is called a polar equation. So you have a coordinate equation. These are polar equations. For example, r equals 2 sine theta is a polar equation because it has r and theta in it. Just like when we graph a graph on the coordinate grid, over here, it has an x and a y in it. It's the rectangular, the Cartesian equation. A polar graph is the set of all points whose satisfies the coordinates r theta, and it satisfies that given polar equation. So a polar graph is the set of all points whose coordinates r theta satisfy a given polar equation. So let's graph the polar equation. So this is a polar equation. Now you're like, wait, it doesn't have a theta in it. Remember, sometimes we graph on the coordinate system over there. It just says x equals 3. You just graph the vertical line, x equals 3. There's no y. So sometimes when we graph on the x and the y axis, when we graph our equations, it just says x equals or y equals. It doesn't have both. Same thing in the polar system. You can have a polar equation that has both x and theta, or r and theta, or sometimes you just have an r, sometimes you just have a theta. That's how we're keeping it simple. All right, back in the day when we didn't know how to graph, you just made the first, in Algebra 1, you made an XY chart. Okay, so if we don't know what to do, let's make an R theta or theta R table. Theta R. And then it gives you R comma theta. Now this setup is a little bit different because normally we'd XY, and then in the coordinates, it went XY. Remember, we generally do theta first, like we think about graphing theta first and R second, but in the point, R comes first, theta comes second. When we do this, we think of theta as the independent variable. Theta is that independent variable. It can just keep changing, okay? It's your independent variable. So let's just list a couple thetas independently. Pick them out of the clear blue sky. Just like when we did graphing x and y, I don't know, some of the x's we like to use were -1, -2, -2, -1, 0, 1, 2. Same thing, right? We just selected them. Let's just select theta. So 0 degrees, I like degrees, but you could use radians. 30 degrees, 180 degrees, I don't know, 225 degrees. Dot, dot, dot. I just picked some random points. Okay, if it says r equals 3, doesn't matter what theta is. According to this equation, regardless if it's 0 degrees or 30 degrees, the radius is 3. 3, 3, 3. R equals 3. So this is the coordinate 3, 0. This is the coordinate radius 3, 30 degrees. This is the coordinate 3, 180. This is the coordinate 3, 225. Okay, let's just graph those and see if we have enough points to understand the shape of the whole equation. Okay, so let's plot 0 degrees, that's on the polar axis, with a radius of 3. So 0 degrees, 1, 2, 3. Okay, check, I just graphed that one. 0 degrees, radius 3. 30 degrees, radius 3. 1, 2, 3. 180 degrees, radius 3. 225 degrees, radius 3. Now, I didn't give you any negative angles. I could have. How about negative 30 degrees? Negative 30 degrees still has a radius of 3. So that's the polar coordinate, 3, comma, negative 30 degrees. If I plot that, okay, here is negative 30 degrees, 1, 2, 3. If you think about all the thetas, every independent theta, but the radius is being 3, if you connect those dots, you have the polar graph of a circle. So what you have, the equation here, r equals 3, is the graph of a circle with a radius of 3. So you've graphed circles on the x and y plane. Now you've just graphed a circle in the polar plane. R equals 3 is a circle of radius 3 at any theta you choose. Okay, so there's a circle equation. Okay, let's look at the next simple one. Let's figure out what that's going to be the graph of. Now remember, we're starting off with simple polar equations. So let's make our table, because remember, if we didn't know what to do, we make a table. So our tables for polar graphs are theta, r, and then the point is r comma theta. Now you don't have to fill this in. If this is enough and then you graph, that's great. Okay, this time though, because theta says 3 pi over 4, we independently in this case fill in r. So we need to come up with some different radius. I don't know, let's go radius of negative 2, maybe a radius of negative 1, a radius of 0. That's not your bell, that's the bell here. 1, 2. Okay, doesn't matter what the radius is. Our theta is 3 pi over 4, 3 pi over 4, 3 pi over 4, 3 pi over 4. That's getting sloppy. 3 pi over 4, 3 pi over 4, 3 pi over 4. Okay, so here's the point. Negative 2, comma, 3 pi over 4. Let's graph that. So remember, you do theta first. Find theta. 3 pi over 4 is 135 degrees, and I need a radius of negative 2. So that shoots me not here, but back here, a radius of negative 2. That's that point. Now, we need 3 pi over 4, 3 pi over 4 with a radius of negative 1. That's that point right there. 0 with a radius of 3 pi over 4. Well, if you're right there and it's a radius of 0, you don't go anywhere. You're on 3 pi over 4 and a radius, boom, right there. You don't step anywhere. You're right at the pole. 3 pi over 4 positive 1. 3 pi over 4 positive 2. A theta of 3 pi over 4 positive 3. If you connect these dots to make the graph, you are graphing a line. So that's the equation for a line. Okay, so to summarize, maybe we can summarize a bit. What are the two major equations we know and the shape of their graphs? So this is our final thoughts about the graphs, because we only know two basic ones. If you have r equals a number in the polar system, that is going to be the graph of a circle. Graph a circle with the radius of that number. If you have theta equals a number, remember that number represents an angle, that graph is going to be the graph of a line. Okay, and it's opposite right. So both directions, like a whole line, not just half the line, the whole line. Because remember, you can have a negative radius and a positive radius. All right, that's good for 9-1. So the good news is by doing this video is it should be linked on my calendar, right? So if you didn't catch anything, or if you want to re-listen to any part, or go over anything, you can just re-watch the video. Make sure you get some polar graph paper. Grab several pages because you're going to have it for the next couple days for your assignment. And I will say this, it's a lot more fun when you guys are here. This isn't easy to do. So hopefully you were able to get most of the understanding of the material. But please just help each other, and I should be back shortly. So thanks, and have a good day.